to the computer screen and we'll take a look there. We've installed our extensometers. We've got everything where we want it. So now I'm going to zero my extension. You can see it's not zero. It doesn't say here, but I'm going to go ahead and balance my extensometers. My transverse extensometer, I will need to calibrate because we don't have a fixed gauge length on the transverse extensometer. Our gauge length is defined as the width of the specimen. So in this case, our width is 12.34 millimeters. And I can calibrate that. So the transverse extensometer must be calibrated for a gauge length equal to the width of the specimen. If all of your specimens are identical, then this only needs to be done one time, but ours will vary, so we'll do this for every specimen. All right, so now everything's zero here, and we're ready to start our test. So I'm going to click Start. And away we go. We often get a little bit of oscillation at the beginning of the test as everything sort of settles in. So we are in the linear elastic region of the test. This is where we'll want to get our information to calculate Young's modulus and Poisson's ratio. You can see our indicators are live. The strains are increasing slowly. And we're going to be watching for a transition from this linear elastic region where if we remove the load, the specimen will recover to its original length. And now we're entering the plastic region. And from here on out, this plastic deformation will not be recovered if we remove the load. Not much to see on the specimen at this point. Our load is still slowly increasing. And until it starts dropping, we won't really see anything happening on the specimen. Once it starts dropping considerably, we should be able to observe necking behavior, which is a narrowing, hopefully, in the gauge section. See, our load is still slowly increasing, starting to level off. So we're still plastically deforming fairly uniformly along the gauge section. Once we start to see that load drop, it means that the deformation is starting to be concentrated in a smaller region, and that's what we call necking. It looks like it's starting to drop now, so let's see if we can observe that. But it looks like it's starting to begin in our gauge section between the knife edges of the extensometer. Should be able to see it right here. If we look at our plot, we can see that the load is decreasing more rapidly now. Should be getting pretty close to fracture at this point. All right, so there's our fractured specimen. We'll pull that out and then measure between those two marks, which you can see on the specimen, and see what our final length is. Okay, I've taken the aluminum specimen out of the grips that we just tested and basically reassembled it at the fracture surfaces. And you can clearly see our marks that we put on the specimen before the test that were 50 millimeters apart. So now we're going to measure and see how far they are apart after the test. That's our final length. And I'm going to use my steel rule here. And I would say that that is 58 millimeters. Okay, we're going to move on to the steel specimen now. So I'm going to enter my user inputs. This is A36 steel. Call that A36 number 1. Our width was measured to be 12.47 millimeters. And our thickness was measured to be 6.24 millimeters. And our 50 millimeters is the distance between the marks that we put on the specimens. All right, so I'll click Next. And we're going to load up the specimen now. Just kind of follow these steps here that you see on the screen. And we're ready to go ahead and start. So it's a little difficult to see, but we can see right away that the slope is much steeper on this material, which means we have a much stiffer material. All right, looks like we've yielded. You'll see that there's a interesting little double peak here. We have an upper yield and then kind of a lower yield point. So after this initial yield point, we have some realignment of the microstructure. And once that's complete, we really start to pick up some load here. The aluminum, once we yielded, the load didn't really increase very much. But with the steel, you can see that it's still increasing quite a ways. And like the aluminum, we won't see much action in our specimen until we've reached the maximum load and starting to deepen. So our load is still slowly increasing. We haven't leveled off yet. These are both very ductile materials. We get a lot of elongation before failure. When we get to the composites, things are going to change. Now we can see some narrowing between the knife edges of the extensometer. That's our necking behavior. You can see the load is dropping off considerably. And a little bit closer view of that fracture area. Okay, let's pull the specimen out. Let's go ahead and get set up for the composite specimens. And we are ready to go. I've cleared the screen of the aluminum and the steel so we get a little bit better clarity on this specimen. And it'll be obvious why afterwards. All right, so you can see that our specimen just brutally failed. Straight up and snapped off. Compared to the steel, my 90-degree carbon fiber specimen is way down here. So not a lot of strength there and not very stiff. So we'll pull that out now, and I'm pretty sure that the final length will be essentially the same as the initial length, but we'll measure that and verify. All right, I've got the 0-degree specimen loaded up. You can see some things have changed here. First off, I have this polycarbonate glass door installed in front of the specimen. The reason for that will become evident shortly. And then you can see that we've changed extensometers here. This one is a lot more robust and designed to withstand the abuse it's going to take when the specimen fails. It's a little bit larger. It's got a 50 millimeter gauge length rather than the 25.4 millimeter. And that's better suited for composites, which typically tend to be longer. So we have a longer gauge length. Okay, I've got the transverse installed as well, but I'm going to remove the transverse extensometer about halfway through the tests so it doesn't get subjected to the abuse when the specimen fails. All right, I've got everything loaded, zeroed, balanced, etc. And we are now ready to test. See, we're much stiffer. We have enough information to grab Poisson's ratio, so I'm going to pull this guy off. So I don't want to be anywhere near there when that thing fractures. See if we can zoom in just a little bit more here. Oop. Looks like we're getting some fiber fractures. We're getting individual fiber failure, but you can see we're still picking up load. Let's zoom in a little bit more here. So let's take a look. I don't really have a good feel for when this is going to fail. See that our slope is dead linear, other than that premature fracture of the single fiber. And there we go. So, as I said, you can see why we don't want to be anywhere near that thing when it fails. It produces quite a bit of shrapnel. All right, so that's it for Lab 2. You'll be provided with a complete set of data for 12 tensile tests. The equipment will be set up during your scheduled lab sections, so your TA will be able to repeat parts of the process in more detail and answer questions about anything that was unclear in this video demonstration.